And then welcome you all to this presentation, and welcome Professor Trevor Ireland, who you can see is at the RES and Planetary Science Institute, the Australian National University in Canberra. And Trevor, we're delighted to be able to beam someone in from across the ditch. This is the first time that U3A Dunedin, anyway, has done this, and it's a real pleasure to be able to welcome you. Trevor completed his BSc with honours at Otago University and subsequently a PhD at the Australian National University in 1987. Since then, he's held numerous postdoc and professorial positions in both Australia and the United States, including Stanford University and UCLA. He's president of, or has recently been president of the Meteorological Society through 2017-2018, and you'll see also there that he's a member of the Hayabusa Joint Science Team and the Osiris-Rex Science Team. He also leads the shrimp team, and I'm going to leave Trevor to describe to you what shrimp is and what it does. So Trevor, welcome. The digital floor is all yours.
Thanks, Doug. Well, first, thanks for having me there. I would have preferred to have been there. I much prefer engaging with a real audience, but these days, you know, everything has gone rather strange, and travel is not going to be an option for some time to come. So thinking back, you know, whoops, what have we got? Why can't I show the screen? Oh, I see why. So, should I show window? Okay, so why am I showing this slide? Listen to that all day. And I believe Queen played in Dunedin as well. So the question to mull over for the course of this talk: why am I showing you Queen playing in Sydney this year? What connection has it got with this talk? And I want to be very specific. And if somebody can come up with a specific answer, I've got a little prize for you, which I'll get your name and address afterwards and send it to you. So. We'll see what happens. Anyway, remember that. So I am, oh, go away. Am I in the right one? Let me keep going down. All right, like... so this is all about asteroid return missions. And so this is taking space missions out into an orbit around the sun and visiting what's going on around the place, and trying to land on one of these targets, grab a sample, bring it back to Earth. And so, in large part, we're interested in asteroids because they're the source of meteorites. Meteorites are important objects, which, you know, they're what the Earth accreted from, and most of those meteorites are actually coming from asteroids. And the asteroids are largely coming from the asteroid belt between Mars and Jupiter. And effectively, that asteroid belt is being bullied into its present shape because of Jupiter. And so effectively, it's the solar system dust bunny. It's the stuff that was left over after the accretion of all the rocks. And so if we can get back to that material, we can actually see what the whole solar system was made of. Because as we look at the Earth, we see all this material which has been homogenized and cycled and churned up. It's gone through the big sort of solar system washing machine, and everything's been homogenized, and we want to see what we actually came from. So at the moment, there are 2 asteroid sample return missions underway. One being Hayabusa 2, which I'm largely going to talk about today, and the other being Osiris-Rex, which I'll leave out simply because for brevity. So we can look into the sky and see asteroids, and so here we see a couple of images of asteroids, one with the background and up that top left side held fixed, and then we can see this bright object moving across it, and then from the perspective of the asteroid, we can see it marching across the sky. And so when these things were first observed...
Trevor, I'm seeing your title slide, but nothing else at the moment.
Sharing is paused. Resume share. Why isn't that doing? No. Why is that? You're sharing your computer. Yes, bring the shared window to the front. What's going on? Sharing is paused. Why? For some reason, it's not. It's decided it's going to give up sharing.
Ah.
All right, let me stop it and I'll start it again.
Okay.
And come in here, share screen. This one, share. I don't want to do that. So can you see that now?
Yep, that looks great.
All right, so this is, so maybe, interesting thing. So can you see it moving now?
Yep.
Okay, cool. So the top left one is the background stars kept in fixed position, and you can see the asteroid moving across. So you could go back each night and revisit this. And much as you see the planets moving across the sky, so at the moment you can see Jupiter and Saturn in the eastern sky coming up in the early evening, two very bright objects. And they move across the sky. We can see them basically, we can see, and the moon moves across the sky. So do the asteroids move across the sky, and we can see those. And by looking at those, we can actually reconstruct their orbits. And we know by doing that, we can see that where the distribution of the asteroids is, which is shown on that bottom right-hand diagram, which shows a cluster of all sorts of white stuff in between Mars and Jupiter. So those are all the asteroids, which we really like to get samples of all of those, but there is a slight financial constraint on sending out missions to every asteroid. They cost about $250 million a pop, so we're sort of limited these days as to, still a little bit limited as to what we can do. All right, so hopefully that changed. So here's some close-ups. There are a number of missions that actually went out. So the NEAR mission, Eros on the left there, the NEAR mission is the Near-Earth Asteroid Rendezvous. So they went out and visited these guys on the right-hand side, and Galileo on its way to Jupiter got photos of these things as well. So we have quite a few close-up images of the asteroids, but we also have missions such as the Dawn mission, which went out and to Ceres and Vesta and went into orbit around these guys and got really close-up images. So these are fantastic sort of, this is most of the real estate of the asteroid belt. Ceres is about 1/3 of the mass. But one of the things about looking at these asteroids is, you start looking in detail and the images are great, but then you start looking and saying, well, what's that white stuff on Ceres? Why is there white stuff there? And then you're going to figure out, well, what composition is that white stuff? So the remote imaging is great, except that it usually raises more questions than answers. So Doug said at the start that I'm going to start asking you guys questions because I need to figure out how I can get feedback from students and Zoom lectures. So here's 3 images. So who can tell me what the 3 images are? Can we see I might see the chat. So you've got a round thing on the left, you've got a round thing on the right with all sorts of lovely colors, and then a sort of more of a rocky surface in the middle there. Anybody going to hazard a guess? I can't see chat at the moment.
I'll relay any chat responses to you.
Yeah, I think that may have interfered with my sharing or something, but I'm not sure. Have we got any offers?
No.
Come on, the one on the left. You've seen this. Been in the newspapers.
Yep. Kaz says Mars, Moon, Earth.
Wrong.
Okay. Nice try.
The one on the left, it's got a heart shape there in the middle. What was the heart shape? This used to be a planet.
Well, I'm able to talk, which makes it a bit easier, perhaps. Is that ice?
Yeah, that's ice. And it's a very weird ice. That's one of the things which I'm showing this for to you, because the ice is not ice as we know it. It used to be a planet. It's only one of those. It's only one demoted planet. As they say, it got Plutoed.
How about frozen sea? Frozen salt water?
No office. Well, okay. The one on the left is Pluto. So this is the flyby in 2015, the New Horizons mission flew by Pluto, and it does have this heart-shaped ice block on the right-hand side of it. And anybody who's going to Pluto now would be in trouble, because all the school kids would be bringing out the heart, and you'd have to shoot Pluto through the heart. Anyway, the intriguing thing about Pluto is that white stuff in the middle is not water ice, it's frozen nitrogen. And so we didn't know this until you actually do spectroscopy on that ice. Otherwise, you just see this nice icy body. And the one on the middle is, let's move on, is Titan. And that is one of the moons of Saturn. And there was a Huygens lander, went down in 2005, I think it landed, and took images of the surface. And you get these images, and you put this in front of people, and you can see that these the blocks of stone down the front there look rounded, as though they've been put through a river. And so I'll ask my geology class, what are those rocks made of? And invariably they'll come up with the most common rock type on the surface of the planets, which is basalt. And it's not basalt. And Titan exists at the balmy temperature of 95 Kelvin. So that's about minus 180 degrees Celsius. And so these are actually, the next thing you could argue, well, these might be water ice on the surface of Titan. And that's what I believed for a while. And then they actually started doing spectroscopy of the surface. And these turn out to be some weird sort of composition of an organic ice. So Titan is covered in these organic oceans of liquid methane and propane. Very different place to what Earth is. And then the guy on the right, this beautiful color image, it's got lots of volcanoes on it. This is Io, one of the moons of Jupiter. And it is so close to Jupiter that it actually squeezes like a piano accordion. And in doing that, the friction causes heat on the inside and creates these volcanoes. And so the rings around that beautiful reddy orange ring that you can see is actually a sulfur deposit around. It's sort of like going to Rotorua and seeing the hot pool, same sort of thing. There's probably some arsenic there, maybe some sulfur and so forth. So you get these beautiful colors set up. So the take-home message from this is that we can get a lot of images of these neat places, but until we can really get samples of them, we can't do detailed analysis, and we're left with the spectroscopy to say roughly what their chemical composition is. And we can do that with the asteroids as well. So rather than looking at them in the visible, we can look at them in the infrared. This is a complicated diagram, but the take-home message in that right-hand diagram is there are squiggly lines there, which are basically spectra of looking at the asteroids. And there's a thing called surface reflectivity, which is basically how bright they are. And then there's some wavelengths there. And so 0.5 microns is roughly greenish or thereabouts. And then it goes up to 2.5 and color disappears red at about 800 microns. And then this goes into the infrared colors. And we can see that in the infrared, we can actually see for that thing called Vesta, we can see some big dips. And this is because Vesta has a lot of pyroxene on the surface. So we can sort of get a rough idea of mineralogy just by looking at these asteroids. And from that, we can see that there are different distributions. So this is the distance from the sun versus the percentage of asteroids. And then you can all those different asteroid types and the spectra we can assemble and say, gee, the main belt asteroid is actually zoned. We can see there's S-type in the inner part, M-types, which are the metal ones, and C-types are the carbonaceous in the outer part. So we know there is structure going on in the asteroid belt, and we'd really like to understand that. So our avenue for a bit more understanding comes from meteors, and with the advent of mobile phones and the video cameras and people taking images out the front of their cars and things like that with GoPros, we have some pretty spectacular sort of entries of meteors coming in. So this one on the right is an asteroid type body blowing up in the upper atmosphere and then streaking out. And this was taken when somebody got a little bit bored with the football match they were taking in Denver in the States. So we get that stuff down to Earth, and of course there's a number of famous meteorites, and one of the more famous ones is, poor old Annie Hodges, who was lying in bed one morning and basically something came through the ceiling and landed on her side. And that's the doctor there is showing her the bruise on her side as this thing bust through her ceiling and cracked into it. And her husband, and that third one from the left, is actually, and the policeman in the second image and the first one, they're actually holding the meteorite that came down through the ceiling. And there's all sorts of stories like this. One of my personal favorites is a family who was sitting down to their meal, and they were saying grace, and all of a sudden a meteorite comes straight down through the ceiling, straight through the table, and disperses dinner. So you can interpret that how you wish. So from the meteorites, we have a variety of rocks. So a meteorite is a rock coming in. It's an extraterrestrial rock. And what we see are a lot of iron meteorites. And these are quite distinctive because they are composed entirely of native iron alloys. And these don't exist on the surface of the Earth except in a few strange places. But we know where those ones are coming from, and they are quite distinctive. The distinctive characteristic of meteorite iron is it contains a lot of nickel. And so if you see anything from the Earth, it doesn't contain nickel. So if somebody brings this in something which they think is a meteorite, we just analyze it and see how much nickel it is in it relative to the iron, and we can tell pretty quickly. On the other hand, we have a lot of stony meteorites, and those things called chondrites are called chondrites because in that thin section there, you can see these little round molten silicate droplet type things. And those are the chondrules. And so those chondrites, the stony meteorites, are the most common of all the meteorites. They comprise about 90% of all material coming in. And so even though we regard iron meteorites as being distinctive, they're not the most abundant ones. It's the chondrites. And in fact, there's one body out there which is producing about a third of all known meteorites at the moment. So that may change with time as different things break up. We'd like to get a handle on that and understand those bodies. But the chondrites are by far the most common. And then in the more rare things are these stony iron things. These are pallasites which have metal and olivine grains in them. Spectacular, make a great coffee table. And then there's the achondrites on the right, which are the previously molten things, the HED meteorites, which we now believe come from Vesta. And then the SNC meteorites, which come from Mars, Shergotite, Narcolite, Chasignite. And we also get lunar meteorites. And I can't own a piece of the moon, but I actually have a piece of the moon in my bedroom sitting on the side, which is a lunar meteorite. So we can get pieces of those things. So these samples are great. These are the poor man's space mission. We get all these samples. The problem is we don't really know where they come from. There's still an argument as to whether SNC meteorites are from Mars, and so this is one of the reasons why we have to go to Mars and bring back a sample. Right. So we can connect up the meteorites quite nicely with some of these asteroid spectra. So remember I said the HED meteorites, Howardites, Eucorites, Diogenites, are associated with Vesta, and that spectra shows why. That eucrite is almost a dead ringer match for Vesta, and that's the only place we see that spectrum. And then we see that the S-type asteroid spectrum is similar to the stony iron, and C-type is similar to carbonaceous. And so there's some interesting corollaries there, and we'd like to know, do those actually correspond identically? What's actually going on? We don't actually have a chondrite on that right-hand side. How do the chondrites fit in into this stuff? And one of the main reasons why it's difficult to actually match these things up is because the asteroids have been in space for a long time. They get space weathering from solar wind and things like that. And we just don't know whether, and when when a meteorite comes in, that all gets burnt off. So we're not actually looking at, we're looking at oranges and peeled oranges. And so sort of matching them up is not necessarily that straightforward. So we would like to get samples. Where do the ordinary chondrites fit in? The C-type asteroids are very common. They're the most common type of asteroids, but the carbonaceous chondrites, which we're going to try and match them up with, are quite rare. And so we really want to bring these samples back for detailed laboratory analysis. All right, so how do we get an asteroid back to Earth? Well, the Japanese Aerospace Exploration Agency, JAXA, took this on, and their first mission was the Hayabusa mission, which flew from 2003 to supposedly 2007, but actually lasted until 2010. So the spacecraft itself, it's going to sample, so you need a sampling mechanism. And so Hayabusa actually means falcon in Japanese. And so you can see from the little cartoon there that this thing has the solar panels, which look like wings, and then the whole spacecraft comes down onto the surface of the planet. You can see the sampling horn coming down underneath it. That touches down, and then it's got a really sophisticated sampling mechanism, which is basically a little BB gun blasting away at the surface to try and excite material up into that sampling horn and into the chamber, and then it goes away again. So all this, it comes down slowly and then bounces back and away. And it's on about that sort of time scale. Now, the Japanese set this up as a technology demonstration. So for the first time, they used iron engines to drive out along to the mission. They worked pretty flawlessly all the way. They had autonomous navigation, so they take images of the stars and so use stellar position navigation. And then, of course, they have to bring a sample back to Earth. And otherwise, I'm not interested. So to cut a long story short, I'm not going to go too much into the mission. There's some issues as it went out. But this is the first asteroid that they went to. This is the first example of what we now know as a rubble pile asteroid. So this is like your debris slope or your sedimentary deposit of all sorts of stuff being amalgamated into an asteroid. So there was conjecture that these existed before, but nobody had actually seen it beforehand until we actually got there. And so I went up to Japan at some stage in 2005, looks like about October or so, for a landing site selection meeting. And so if you ask a geologist and you've got all this nice smooth area here and you've got all this rough stuff, and so the geologists say, well, we'd like a sample of both. And the engineers say, you can choose point A. So we chose point A. And so then we went home. And so then it, oops, kill that. And so then we, so then the spacecraft decides to go, is sent on its way down. So it's got an autonomous approach from home position because it's on the other side of the solar system. So we can't control it. We can just tell it, go through these series of instructions and go down, land, grab your sample, come back, and then tell us what you got. And so the first indication we had from this part of the mission was that the spacecraft stopped at plus 17 meters. And it's like, what does that mean? And so you ask the mission engineers, it's like, what's plus 17 meters above an asteroid? And they scratch their heads and it's like, guys, it hit the asteroid. And so the touchdown effectively occurred before it was expected. Because it wasn't expected, they hadn't taken the safety interlock off the gun. And so the gun didn't fire. And so it went down, touched, and then left. and return to home position. So then we looked, okay, well, we'll have to do a bit better next time. So they examined all the software and things like that. And so then there's 3 possibilities of touchdown. So it's not all lost. So touchdown 2, we start the approach initiated coming down, and then we heard nothing. And so there was, what apparently happened is that after the second touchdown, and this is pieced together after the fact, all the chemical thrusters fired at once. It was totally out of control. There was no stabilization. We lost the alignment of the solar panels to the sun. We lost the alignment of the antennae to Earth. And so this thing was basically AWOL for a while. And so they tried for 2 weeks to recover this. It was spinning out of control. So we basically lost the departure window to come back to Earth. So that's why it came back in 2010, not 2007. It was left to basically spin chaotically for 9 months. And so the idea was that, well, hopefully this will basically all, rather than wobbling and being totally chaotic, it'll all go down to one single rotational mechanism, and then we had a chance of actually recovering it, which we did, and basically came back for the 2010 arrival. So the spacecraft came back into Woomera, which is the test range in South Australia. Because it was 3 years longer, the batteries may not have been quite right. So you know, it's like the toy that survived 3 Christmases too late and was given out. The battery's okay, and so they decided to separate as late as possible, which meant that the capsule was coming in as well as the main spacecraft. And in fact, the capsule was only about 400 meters ahead of the capsule. So obviously I've got a nice video of that coming in. So the little bright dot underneath is actually the space capsule, which is what we're interested in. And then the spectacular light show above that is basically the main spacecraft burning up in the upper atmosphere as it comes in at 12 kilometers per second. And this is totally rocket science. 12 kilometers per second. If your re-entry is 1 second out, you enter 12 kilometers, you pick it up 12 kilometers downrange. And so one of the NASA guys who I was with for this re-entry was basically counting it down, 5, 4, 3, 2, 1. Okay, you should be able to see it now. And there it was. You could actually see it. And so we knew, well, that's a good sign. It's probably going to end up pretty close to where we want. And all you could see at the end of this was, you know, the last thing you could see is this thing glowing slightly red as it cools down. And then the hope is, well, the batteries are operational, because then we can, the radio beacon will go out and the parachute will open and so forth. And everything worked flawlessly. So about 2 a.m. the helicopter went out, and that was the image on the left of the sample capsule on the ground. And then there's this lovely image on the right-hand side of what it looked like. And this is after, you know, 7 years in space. That's our sample return capsule. And that's got our samples in it, hopefully. And we didn't know that we had samples. So this is all wrapped up, taken, boxed up, and then shipped back to Japan for examination. And the first thing that was tried was to actually stick a spatula in there and scrape around the inside. And then we found various particles of aluminium, which are just the machining remnants. But then we start picking up those things on the red arrows, the couple of rocky fragments, and pretty quickly they picked up that there's olivine, pyroxene, plagioclase, and trowelite, all sorts of minerals. Olivine and pyroxene are those iron magnesium silicates we can see in asteroids. Plagioclase is also a common mineral. It's a very common mineral in granites on Earth. And trowelite is an iron sulfide, which is only an extraterrestrial mineral. You do not see that on Earth either. And so we got one definite extraterrestrial mineral, and then we can look at these particles, we can chop them up and look at them and get more detailed images of the mineralogy. And the major conclusion was from this was that the material we got back is likely extraterrestrial. So this is great because we know the gun didn't go off, and so this is just accidental entrainment of dust stirred up when the spacecraft landed. And with the chemistry is sort of unique, so that red star on this right-hand diagram, don't worry about what it is. It just shows that the Itokawa sample, which is the blue diamond up that top side, corresponds with those red circles, which are LL chondrites. So this is one type of chondrite, and there's a green type of chondrite there, and there's a yellow type of chondrite. And so we've got a good correspondence with the red ones. And so we basically said, well, this is an LL chondrite, which is a chondrite with low iron, and as opposed to the high iron ones in the yellow there. And the proof that it was actually extraterrestrial comes from some of the stuff I do, which is very detailed, and why we need samples coming back. And the real take-home message here, again, complicated diagrams, is the distinction between these samples, which are black circles, red squares, and blue circles, from the crosses down below. So the TF is terrestrial, and basically we can see that these Itokawa samples in black, red, and blue are distinct from the terrestrial samples. So this is oxygen isotope compositions, and these are characteristic and distinctive as being extraterrestrial. And so that was one of the big confirmations. So now we know that, you know, that the oxygen isotopes, and everybody does oxygen isotopes with meteorites as well, there's a very good correspondence, and we're very happy to say that this is, and with the chemistry, that this is an LL chondrite parent body. Now, one of the most intriguing things I think results we got out of this mission, and again, sorry that these are complicated, but I'll just give you the take-home message. We can actually see the addition of solar wind onto these particles that came back. So if you're out in space, you're continuously bombarded by cosmic rays, solar wind, all that sort of thing. And so the longer something is exposed to solar wind and cosmic rays, the more of the products they actually have. And we found that the solar wind was actually very close from Hayabusa, was actually very close to the solar wind composition we've measured from the Genesis mission as well as from lunar samples. And it had very little cosmogenic or long-term exposure to galactic cosmic rays. And so this means that Hayabusa was very young. In fact, it was less than 8 million years old. And 8 million is nothing in terms of solar system ages. The age of these asteroids is of the order of 4.5 billion years old. So they're very old, and that's when Earth was forming as well. So what it's telling us is giving us an indication of the dynamics in the solar system, and how young things can be, and how ongoing processing is going on in the solar system. And there's the exposure age. All right. So where do ordinary chondrites fit in? That was one of the original questions. Well, Hayabusa showed that the S-type asteroids include chondrites, and chondrites have a lot of metal in them as well, and so metal and iron, magnesium, silicates. And so we've got that one nailed down. What we don't know are the C-type asteroids, which are very common, versus carbonaceous chondrites are very rare. And so that was the basis for deciding, okay, we'll go out and do another mission. Now, the Hayabusa mission was incredibly popular. There were 3 motion length pictures released regarding Hayabusa. And they got, you know, what's his name? The famous Japanese actor is involved in this and playing various roles. And it's all very entertaining. And so all sorts of things came out about Hayabusa at the time. This was great. And so there was a lot of popular support for this. And so Hayabusa 2 was basically building on this mission to Itokawa to visit another near-Earth asteroid. And this time we're going to a C-type asteroid. And this is the asteroid which is now known as Ryugu, which is also on a sort of an Earth-crossing Earth-crossing orbit. So the advantage of these Earth-crossing orbits is we can just basically take off, time out departure, and we're already on the orbit of this of one of these asteroids, and then we just use our ion engines to accelerate and to match the speed. So Hayabusa 2 launched in December 2014 and arrived in June 2018. It departed after a year or so there, and it's going to return later this year. So that's one good reason to give this talk, because now you can see what we're going to be doing as we've seen from the Hayabusa mission, what we can actually do with the return samples from Itokawa. So Hayabusa 2, similar technologies. It's going to do the same touch and go. It's got some cameras to drop off on the surface. Hayabusa 1 had those as well, but they missed when somebody had to decide when to throw them, chuck them at the asteroid, and it didn't work quite as well. And there's a couple of new experiments as well. So I'm not going to worry about telling you about the details of those. We'll come back to those. And so here's the launch. I went up to Japan in December 2014. And this rocket is about 50 meters long. It's a 500 kilogram payload. And always a good way of checking out your speaker system as to getting one of these things going away. I was just taken on my iPhone from the car park where we were sending to watch it, which is why you can hear other people whooping and hollering. And then you start to hear sonic boom type stuff as it accelerates away. So, mission goes around, it orbits, it sort of goes in a funny orbit which goes closer to the sun and then does a whip around from Earth, get a bit of acceleration from Earth. And then in about January of 2019, we get 4 pixels which is Ryugu. And so then the autonomous navigation takes over and it goes in. And here's the approach. And so, you know, this goes from 4 pixels to basically 200 pixels in the last 4 days or so. So, you know, this is quite a small object. It's only about 900 meters across. And you can see it's sort of a diamond-shaped object. Again, it looks like a rubble pile. And so there's our diamond-shaped profile. It's got craters in it. It's got big boulders on the surface. And it's got some troughs and ridges and so forth. So this is a slightly different object from Itokawa. So here's my friend Makoto Yoshikawa, who's one of the main leaders of the project. He's holding a couple of 3D inkjet models of Ryugu, and it's diamond shape and profile, but from the top it's actually round. And so this looks as though this thing's rotating and redistributing stuff down, and so it's accreting at the pole, at the equator, and so you're getting dust aggregated down there. And so this may be just that it's an older type of object than Itokawa. Itokawa may be 8 million years old and very young, still basically just a big assemblage, whereas Ryugu has had a lot more time to consolidate. So we've got lots of questions about it. Foremost of all is, where do we land? Because we want to get a sample from this. And there's lots of boulders on the surface. And so this was a bit, what are we going to do about this? So we decided we need a lot more close-up images. And so I think this one shows a blow up. And so that doesn't look too bad until you see the scale bar down the right side. It's 10 meters. So this is 10 meters across. It's probably 10 meters high as well. If you have a sort of a 2-meter spacecraft going down in proximity to that, no good is going to come of it. So you try to search the surface of this asteroid, trying to find places where there are no boulders which are going to interfere in your recovery. And so there are a couple of close approaches, and on one of these they dropped off one of the Minerva cameras, and so this is on the bottom, the Minervas are these little things up here. They're like little flying cockroaches with GoPro cameras attached, and so they have the little feeler arms which they can flick and they can move. But these are the images they actually got from the surface, so there's a nice sort of, I don't know, iPhone type image, very wide scale, image going on there, quite spectacular looking. And these are the first close-up images of the surface, and the bottom right one is actually the spacecraft looking down onto the surface as it approached. And so now we're getting images down to about, this is a 1 meter scale bar, so we're getting down to a few centimeter resolution. And so a lot of these things we use to map out. We also dropped this box called Mascot, which is an in situ imager. And so you can see it leaving the spacecraft in this right-hand image, and the square box is which goes down. and it was dropped off into that general region there, those two big boulders on the left there. And here you can see in that middle image, you can see the sun behind, and you can see the image of, or you can see the shadow of Hayabusa 2 as it comes in. And so Mascot does very detailed photographs from the surface, and so we can see things that maybe look like aqueous alteration. We see weathering and fracturing and all the things that geologists like looking at in terms of rocks. And yeah, we think it actually does look like carbonaceous chondrite, and so it's going to be rather interesting to get this thing back. And of course, carbonaceous chondrites are really neat rocks because we suspect that those are the main delivery of volatiles to Earth. So that's where our oceans come from, that's where all the organics come from, and these may be the seeds of life. So a lot of people are very interested in these types of meteorites. And so out of all these, so, you know, bit of examination of all the areas that were examined, this L08 was selected as the landing site. There's still a bit of avoidance of boulders, and so they wanted some more close-up images of this area, and so they did a final approach to 20 meters, which was actually going to use up the fuel, which would have been, say, the third touchdown. So in doing this final approach to 20 meters to try and get the better resolution imaging, they gave up the third opportunity. And so finally, this is the approach, and taking those images, and so this is down to 1 meter resolution, and it looks as though this is a good place to go and visit. Now, actually, this turned out to be the intermission in the mission, where everybody could go off and get a cup of coffee for 30 days or thereabouts, because Hayabusa and Ryugu went behind the sun. And so if you're behind the sun, you have no radio transmission. So from November 2018 to 2019, there's no communication. We just basically put everything to sleep and waited. And so then we've got the sampling attempt actually delayed until early 2019. And so this is the touchdown before and after shot. So the TM in this slide is actually a target marker. It's just basically a reflector. So we can use that to guide into the surface. And that purple ellipse is where we're trying to target. And that's the size of the spacecraft. So you're trying to target well within the realms of the spacecraft. And I think we've succeeded pretty well, because this is the after shot as it leaves the surface, and you can see where the rocket engines fired. They've blown away some dust and so forth. And this shows that we're pretty much perfectly on target during the sampling. So we're very hopeful that we've got the sample from that one. Everything seemed to work perfectly. Then we have this other part of the mission called the SCI, which is not to be mentioned when you get on aircraft, which is the small carry-on impactor. And so this is basically blasting the surface of the asteroid. So here's a little animated GIF of what happens. So this is Hayabusa coming in just above the asteroid, releases the SCI, and then this thing explodes and shoots a bullet down into the surface of the asteroid. So you may have seen this in the news. It was like JAXA blows up asteroid or explodes asteroid or something like this. And it wasn't quite as bad as that, but it basically, the idea is to get a fresh sample from the surface, and doing that, you blow away all the solar wind exposed material. And then the idea is you go back down into the crater and get a sample. And believe it or not, I was somewhat surprised that they decided to do this, because if you have one sample already in the sample return capsule, do you want to risk that by trying to go down again? But anyway, they did it, and that's where the crater is, and that's where we're going to try and go. And during this explosion, they actually sent out a little camera to be viewing what was going on, and the actual main spacecraft scuttled around to the back of the asteroid, so it didn't get hit by any debris accidentally. And so this little bottom right image you see, there's an inset there that's just got a wisp of material coming up, and that's all it was. You know, it didn't stir things up too badly. So, but we could see it actually worked, and got the images back. This is the before and after images, and so this is the before on the left, and you can see a variety of boulders. So you can look at that big boulder on the right hand side, and just to the left of that is where this thing's hit, because you can see sort of 4 rocks which have been badly disturbed in that explosion and basically moved out. So that all looks good. We've located the target site and everything. They spent a bit of time trying to find this, of course. And here's the video of actually going back down into this crater. And so it's going in, and you'll see the sample horn come down in a minute. There it goes, and it's going to touch down, and then bang, it hits. The bullet fires. Pretty sure we get a sample out of that. Goes up the chamber, and we seal off the sample return chamber. So that all looks extremely good, and hopefully we really do have a sample coming back out of that. It slows down again. So the mission is completed at the asteroid. So at the moment it's on its way back. It departed on November 2019. It's back in December this year. So it's got another 4 or 5 months to go. And then we're going to get the preliminary examination in Japan in early 2021. Now, COVID has certainly thrown a spanner in the works of all this, because A, the Japanese have got to get into Australia to go to Woomera to collect this thing. And B, we'd all like to go to Japan to be part of the preliminary examination. So it's not really clear what's going to happen yet. So I don't know how it's all going to pan out, but logistically, the Japanese are planning on spending 2 weeks in Australia for a start off in isolation, which they have to do before they come out to South Australia. Hopefully all that works well. So in perspective, why are we doing this? Well, we're trying to find this link between meteorites and asteroids, understand what the distribution of different types of asteroids is in the asteroid belt, and match up our meteorite inventory, if nothing else, with what we have from the asteroids. Where are all these things coming from? In sort of understanding that, we can sort of examine some of the aspects that, why are these asteroids coming into Earth? What are the prospects of us getting wiped out like the dinosaurs got wiped out? What are the physical properties? Can we do a Bruce Willis and blow up an asteroid, which nobody thinks is a very good idea at all? All these sort of things are at play here. Right, so that's pretty much it. I think we've finished on time. So back to this thing. Right, anybody got a link? Doug, you can tell me, has anybody got a link between Queen and a space mission?
No.
Nobody.
No one has suggested anything via chat for that. I'm not sure that they actually saw the video of Queen right at the beginning. Trevor,
all right, so I'll play it all. I just love this anyway. It's great. So I'll go back to the beginning. Play. So I believe you guys heard this in Forsyth Bar Stadium as well. I think Queen was playing there. So I have chose the hint is that it's related to the guitar solo.
Well, I wasn't in Forsyth Bar. I don't know if any of our other listeners and viewers was.
Who's the guitarist for Queen?
Brian May.
Brian May.
So, I had the privilege of putting these two images together for the first time, separated by a time interval of about 13 minutes. And it's exactly what the doctor ordered. because here we have a beautiful stereo image of Ryugu, the very first in history, right? And it's best if you have a viewer like this, a stereo viewer, to see the stereoscopic effect. But this is it, so hopefully you will find a way of showing this. We can project, if we come to see you, we can project this in 3D and your jaws will drop. But this is beautiful, and we hope that you will enjoy sharing all these images and we can put them together. This was easy to do. He told me not to say this, but it was very easy because the illumination is great, the angle is perfect, and you put the two next to each other and you have your stereoscopic image. So I'm so happy to be working with you guys and to contribute anything you want. But Astro 3D rules, okay? God bless, and good luck with the project.
Thank you, Brian.
So it turns out Brian May is an astrophysicist.
Yep, there were a couple of our viewers indeed got that. Their answers appeared on the in chat. One person says, I was at Stadium and he's an astrophysicist, and someone else also nominates him as an astrophysicist. Yep.
Yeah, that's exactly right. So I've got a present for winning that. So I'll send it to I can send it to Jared and he can hand it on,
yep,
or something. That's probably the easiest way. So 2 people got it?
Yep.
Okay, I'll send 2 presents. Maybe
Wonderful.
3 for one for you, Jared. So, right, so that's it. So Brian May actually does these astrophotography things. So there's the stereo net on the other on that side, but you can actually, if I can get blue and red glasses, if you get some blue and red glasses and you see this presentation, have a look at the one on the right, because this gives you the blue-red. The stereoscope images can be a bit tricky to see, but the blue-red, you can get those blue-red glasses that you quite often get for 3D viewing of movies and things. You'll be able to see Ryugu in its 3D rotational splendor. And I think that's all I've got. So happy to do some questions.
Yeah. Oh, wonderful. Wonderful, Trevor. Let me just have a look at chat, which has vanished again for a moment.
I've vanished it so I can see you guys.
Yeah, I've got just let me scroll through these. Gerard asks, Mars and lunar meteorites, are they splash from the impact? Yes,
so that's one of the interesting things. So to get it off one of these other planetary bodies, you've got to smack it. And so they just don't, randomly fly off. They actually need another big impact to come in. That creates ejecta, and then that flies down, gets into an Earth-crossing asteroid, and then comes in. So yes, that's it. Actually, one of the big lessons out of all of this is the relationship between impacts and all sorts of processes going on in the solar system. So both of these bodies are actually amalgamations of material, which is probably collisions of 2 other asteroids at some stage. The interesting thing about Itokawa is that we only pick up one type of material. So either one was really coming in really fast, like a bullet, and just blew it apart, and then that re-amalgamated, or the 2 bodies that amalgamated were very similar in composition. So we're not quite sure yet. But yes, impacts rule. They rule the solar system.
Okay, there's a very short question here. If I just go back to it. How many asteroids are there in the asteroid belt? Is there?
So there's something like 1 million asteroids over 1 kilometre in size. So there's a huge number of bodies out there. So we're not going to visit them all anytime soon. In fact, getting to the asteroid belt to do a sample return is pretty tricky. So that's why we're picking on these near-Earth asteroids, because dynamically we're staying in proximity to Earth. And even if we go out there, we're coming back. It's not even as difficult as going to Mars. So we basically just jump off. We sort of match the orbit and velocity, join up with it. And then when we're coming back to Earth, we just jump off and come back down onto Earth. So very simple mission in terms of trajectories. Going to Mars, you've got the 6-month travel. You sort of jump off as Earth is approaching Mars on the inside, and then Earth overtakes on the inside. which creates the other big issue of going to Mars. Anybody going to Mars is going there for 18 months to 2 years minimum, because once you've left Earth, Earth's already out of touch, and you've got to wait for a year before you can get into a position where you can jump off Mars and get back to Earth. And so that's one of the big issues of sending a manned mission to Mars. It takes a long time to get there.
Okay, another question. What is solar wind?
So solar wind, if you see images of the sun in total eclipse, you see all the stuff boiling off the surface, and solar jets, coronas, all this stuff coming away from the sun. So the sun is burning up 260 million tons of hydrogen per second and fusing that into helium. All that heat comes up onto the surface, and basically that just boils off the surface and it gets radiated away by magnetic fields. And so we see that coming out to Earth. We've had missions which have gone out. It's effectively mainly hydrogen and helium, but it's also got all the other metals in the sun as well, so everything else that would form the sun. And it comes out at about 400 kilometers per second. So not a big high velocity compared with a lot of stuff. It'd be a high velocity if you were going down to the shop or something like that. But in terms of travel in the solar system, it's not a lot. So it takes 8 minutes for light to come out from the sun to the Earth. For the sun to the Earth, in terms of solar wind, it's, I don't know, it's months to years or something like that. So it takes a lot longer. And people are interested in that because of the solar storms and things like that. And that can get into the Earth. It forms aurora. So the electrons coming along with this solar wind get funneled down at the poles, and that forms the aurora that you see in the southern and northern polar regions.
Okay, thanks, Trevor. I've just scrolled through and wait a minute, there's one last question here. Again, I think from your ration. Is the asteroid belt a planet falling apart, or a planet in evolution, or just stuck at the stage of distributed rubble?
So this is exactly the question that was asked very early on as to what the asteroid belt is. And so some people sort of say, you look at the materials we get from meteorites, and it's like, we get iron meteorites. Well, that's the core of a planet. We get iron metal mixed with coarse-grained olivines. Well, that's the core mantle boundary of this planet. And we see stony meteorites. So these are the surface of this possible planet. But when we look in detail, all the compositions of these meteorites are very different. And so we can pick up a minimum of 200 different planetary bodies associated with this. So while this single planet being blown up, very attractive in terms of the petrography of the different components, in detail, when we look at the chemistry and the isotope compositions, we see a myriad of different bodies. And so we sort of think now that this is Jupiter stopping the amalgamation. So all of these little bodies were formed early on. Jupiter probably occurred because it amalgamated a number of these materials very early on, but then it really got hungry and greedy and gobbled up all the material in its proximity and became the shepherd of stopping all the material from the outer solar system getting into the inner solar system. And so it, in one way, protected Earth from being continually bombarded by material as it accreted, stopped the major accretion of Mars. That's why Mars is so small. It should be a lot bigger if it was just due to the accretion of material coming in. But even the asteroid belt, we think, is a minimum now, because we think if we look in detail, we can see all sorts of gaps where Jupiter has basically ejected material, and that's the stuff coming now flying down onto Earth. But the asteroid belt was probably a lot bigger early on. It's evolved over time, throwing stuff down on top of us, giving us a hard time. But Jupiter also farms and marshals things. You can see in one of those images, there were the Trojan and the Greek asteroids. Those are Lagrange points in the orbit of Jupiter, and that's collecting asteroids, it's collecting comets, all sorts of things like that. any debris, they go into these gravitational wells around Jupiter. So it's all Jupiter's fault. We can blame that.
Wonderful. Trevor, this has been a most extraordinary presentation, I must say. The first word that comes to mind is mind-boggling, and that's in relation to two things. One, just what's out there, and you've given us a fascinating glimpse of what's out there. And secondly, the mind-boggling again, or extraordinary technology that is now available to explore inner space, let's say. And that sort of highlights for me just the fascination that we have with space, and the reason why missions like the ones you've been associated with and others that are ongoing are indeed so fascinating. And I think finally, the ultimate irony is that right at the moment, technology has managed to produce results like that little sample capsule landing in the Woomera Desert, and nothing more than a microscopic particle in the form of a virus is preventing you from carrying on and completing what is indeed a wonderful project.
There's actually an interesting story about that, because the first people that were involved in the recovery of the Hayabusa capsule were Aquis, who are the Australian Quarantine Service. And so their sole purpose was, if that sample capsule had broken over and spilled its contents, they had the spray can of material which was going to kill anything inside that capsule. So, you know, we go out into the solar system, we try to find signs of life, and Aquis is going to kill it. So, but, you know, they can kill the bugs in our spacecraft, they can't kill a bug on Earth.
Yeah, that's rapidly spreading around the world. Wonderful. Well, Trevor, again, my thanks. I'm sure if the audience were there, and hopefully we will all able to be there in the spring when we're planning another series, the applause would be long and loud, and we'll certainly be passing that back on to you. So my thanks. That has just been a wonderful presentation. I do need finally just to mention that there are two more presentations in our two series left. The final Nobel Prizes presentation next Tuesday afternoon on the 2019 Peace Prize. The invitation for that will go out tomorrow. And then a week today on Thursday, Peter Ashworth, the last of the programs that we had to foreshorten because of lockdown, an authorised financial planner who will be giving us some advice on how to sit comfortably in our retirement. So that, ladies and gentlemen, is our presentation for the day. Once again, and thank you, Trevor. Wonderful presentation beamed in from the Australian National University. Interesting, not least of all, to hear how you guys are surviving with a shifting set of goalposts.
Adventure.
Yeah, indeed. So I'll be clicking the end button and looking forward to joining you all next week. Cheerio for now.
Thanks,
Thanks for having me. Cheers.
Catch up later.